The discrete random variable v has probability distribution as shown in the table. Show that the probability generating function of v is as given below. Well, we know that the probability generating function uses the probabilities as coefficients. So we've got 9 over 25, and that will be t squared because the power is the value of v for that coefficient or that probability. So following that, we're now going to get 12 over 25 t cubed and 4 over 25 t to the power 4. Now I can take out a common t squared and a common 25. And if I do that, I then have 9 plus 12t plus 4t squared. You may spot this as being a perfect square. If not, you can use your favorite method for factorizing a quadratic, and you'll find that that is 3 plus 2t all squared. And then to get the expression that we have here, we can put the 25 back inside the square bracket. But remember, it goes inside a square bracket. It needs to be 5. So it's going to be t squared. And then it will be 3/5 plus 2/5 t all squared, which is this expression just here. The discrete random variable w has probability generating function gw of t, which is t times 2/5 t plus 3/5 all to the power 5. In part B, we want to, in part 1, find the expectation of w. The expectation of w is g dashed w of 1. So to start with, we need g dashed w of t. In other words, we need to differentiate this with respect to t. It's a product. So we're going to have the bracket multiplied by the differential of t, which is just 1. So that's going to give us 2/5 t plus 3/5 to the 5 plus t times the differential of the bracket. So when we do that, the 5 will come down in front and multiply. So we're going to have 5t, and then we'll have 2/5 t plus 3/5 to the 4. But don't forget 3/5. Don't forget to use the chain rule here. So we need to multiply that by 2/5. And so what we've got is 2/5 t plus 3/5 to the 5 plus 2t, 2/5 t plus 3/5 to the power 4. So g dash w of 1 is going to be, so here we're going to get 2/5 out of 3/5, which is 1 to the power 5, which is just 1. And then here we'll get 2 times 1. And again, the bracket will end up being 1 to the power 4, which is 1. So we've got 1 plus 2, which is equal to 3. Now, var w is what we want for 2. And that's going to be g double dashed w of 1 plus g dashed w of 1 take away g dash w of 1 squared. Now I recorded the result from part 1 just here because we're going to need that. We can see it appears just here and just here. So we want the second differential. Now the first differential I've got written down here, so we need to differentiate this again. So G double dashed W T is going to be, so this first term is going to be 5, 2/5 T plus 3/5 to the 4, but use the chain rule, so multiply by 2/5. And then the second term here is a product. So 2t, differentiate that and we just get 2. So it's going to be the differential of that times this. So it's going to be twice 2/5 t plus 3/5 to the power 4. And then we're going to have the 2t multiplying the differential of this bracket. If we bring the 4 down in front and multiply, that will then become 8t. And then we've got 2/5 t plus 3/5 to the 3, multiplied by the differential at the inside using the chain rule. And we've got a little bit of simplification here. And so these two terms together become 4 2/5 t plus 3/5 to the 4. And then we're going to have 16t over 5, 2/5 t plus 3/5 cubed. And we're interested in G double dashed W of 1. So this is all going to become 4 because we have 2/5 plus 3/5 inside the bracket. And then that's going to become 1. So we'll have 16 over 5. 4 is 20 over 5. So altogether that is 36 over 5. So we can now put all of this together. And we have, following the formula just here, 36 over 5, add 3, take away 9, which is 36 over 5, take away 6, and 6 of course would be 30 over 5. And so we get 6 over 5. We're now given that v and w are independent, and we want to find the probability generating function of x is equal to v plus w in its simplest form. Now, gx of t, in the case where v and w are independent, is gv of t times gw of t. Now we have the different generating functions from above. So this one was t squared, 2/5 t plus 3/5 squared. And the w was t, 2/5 t plus 3/5 to the power 5. So the t squared times t is going to give me t cubed. And then note that the brackets are the same. And so we can use an index law to multiply them by just adding the indices. And we get 2/5 t plus 3/5 to the power 7. We're now given that y is 2x plus 3, and we want to find the probability generating function of y. Now, one of the things that we should know is that if y is equal to ax plus b, the probability generating function of y is t to the power b And then we have the probability generating function of x, but in here we have t to the a. So the a goes inside like this, and the b is outside here. So in our situation, where we have y is equal to 2x plus 3, we are going to have that gy of t is going to be t cubed gx t squared. So we can use what we know about y, which is this one here, and we get t cubed, and then the gy is going to be, replace the t just here with a t squared, and so we have t squared cubed. So that 3 is the cube that's there already. It's just the t's been replaced by t squared. And then in here, this t needs to be replaced by t squared as well. So that's going to be 2/5 t squared plus 3/5 to the power 7. Now, altogether, index laws, that gives me t to the 6 multiplied by this t cubed is t to the 9, and then we have 2/5 t squared plus 3/5 to the power 7. Now we want to find the probability of y being 15. As we discussed right back at the beginning, that means that when we have y, a table like this for y, at some stage there must be 15. And the probability that goes below that would be the coefficient of t to the 15. Remember, when we did this one back here, we got a 9/25 t squared. So it's the same idea that we're using, just in reverse. So in part E, we want the coefficient of t to the 15. Since we already have t to the 9 in front, we're going to want t to the 6 from inside here. Well, I'm going to think about the t to the 15, including that t to the 9. And then if I want t to the 6 from inside, that means I need 2/5 t squared to be cubed. And if that's the case, with this being a power of 7, we need to have the 3/5 to the power 4. And then we need a binomial coefficient, because remember, this is expanding a binomial, and this is part of the term from that expansion. That's one of the terms from that expansion. And here we can use 7c3 as the binomial coefficient. 3 from there, 7 from here. We could have used 7c4 because we know that the combinations, the lines of Pascal's triangle, are symmetrical. So if we calculate that, we end up with 4,536 over 15,625 t to the 15. So the probability of y being equal to 15 is 4536 over 15,625 as a decimal. That's about 0.2903.